Waves are a series of disturbances which propagate from a source to the surroundings or a destination. They carry along with them a certain amount of energy and information in the form of signals. Let us consider an example where a pebble is thrown into a pond of still water. We see ripples formed at the place where the pebble touches the surface of the water and move outward in circles. A dry leaf on the surface of the water is seen moving up and down in its place. This shows that the water does not move along with the wave. This disturbance in the medium, that is, water, is transmitted from particle to particle. This is due to the elastic forces binding them. Waves not only propagate through liquids, they also propagate through solids and gases. Now, let us look at various other examples where waves propagate through other media. In today's world, communication systems play a vital role. These communication systems involve the transmission of waves to send and receive information. For example, while communicating through a telephone, the sound waves produced by the vocal cords are converted into electrical waves or signals at the source. These electrical signals can be processed in different ways to reach the receiving end. These electrical signals may be transmitted through a copper cable, converted into light signals, and then transmitted through optical cables, converted into electromagnetic waves, and then transmitted through air or communication satellites. The signals received are converted back to sound waves by an instrument at the receiving end. It is not only solids, liquids and gases. Waves can also travel through a vacuum. For example, sunlight travels through a vacuum before it reaches the Earth's atmosphere. Waves are classified into three types: mechanical waves, electromagnetic waves, and matter waves. Mechanical waves are governed by Newton's laws and need a medium to propagate, that is, solids, liquids, and gases or air. Waves in water, sound waves, and seismic waves are some examples of mechanical waves. Electromagnetic waves do not require any medium for propagation. They can travel through a vacuum too. They travel with a speed of nearly 3 × 10⁸ meters per second. Light waves, ultraviolet light waves, radio waves, microwaves, and X-rays are some examples of electromagnetic waves. Matter waves are associated with moving electrons, protons, neutrons, and other fundamental particles. The electron microscope works on the principle of the motion of electrons, thereby constituting matter waves. Let us now discuss mechanical waves in detail. Waves in elastic media, that is air, stretched springs, coil springs, etc., are intimately connected with harmonic oscillations, which constitute mechanical waves. To understand this better, let's consider the example of a slinky. When one end of the slinky is fixed and a slight disturbance is created at the free end, we observe the disturbance carried to the fixed end of the slinky. Now, let us see how sound waves propagate through air. When a sound is produced, it compresses or expands a small region of air at the source, causing a change in the density delta rho of the air in the region. This induces a change in the pressure delta P of air in that region. The pressure causes compressions in the particles surrounding the source. These particles in turn transmit pressure to neighboring particles, which are now compressed due to this pressure. After the transmission of pressure, the particles near the source return to their original positions. This is due to the restoring force of the elastic medium, that is, air. Thus, in the region of compression, an expansion of the air layers takes place. Therefore, a series of compressions and expansions or rarefactions in the region of transmission is observed. Mechanical waves can be either transverse or longitudinal. This depends on the relationship between the direction of displacement of the particles in the medium and the direction of the propagation of the disturbance or the wave. In a transverse wave, the particles of the medium vibrate in a direction normal to the direction of the propagation of the wave. In a longitudinal wave, the particles of the medium vibrate in a direction parallel to the direction of the propagation of the wave. In both waves, it is only the disturbance that propagates and not the particles of the medium. The particles of the medium only vibrate about their main positions. Let us conduct an experiment to understand how a transverse wave is produced and propagated. Let us first fix one of the ends of a string of length 5 meters to a pole. Hold the free end of the string tight so that the string is taut. Now let's jerk the string by moving the hand up and bringing it back to its initial position. The pulse that is created by the jerking action traverses through the string to the fixed end and dies down. The movement of the pulse through the string can be compared to the movement of a caterpillar. The pulse that traverses through the string moves with a certain velocity v. Next, when the hand is moved up and down continuously about the mean position with a simple harmonic motion, a continuous wave, which is sinusoidal in shape, travels along the string with a velocity v. There are two ways to study the wave formed in this process. The first one is by taking a snapshot of the string while the waves are traveling through it. The other method is by marking a point on the string and observing it as the waves propagate through the string. We see that the point moves up and down the mean position. The waveform observed in this process, which is sinusoidal in shape, is a transverse wave. Let us now conduct another experiment to understand how a longitudinal wave is produced and propagated. The apparatus required to conduct this experiment is a long glass tube with an airtight piston at one end. Air with lots of dust particles is trapped inside this tube. Now, let us place this tube in a dark room with a focus light behind the tube. The piston is pushed inside the tube and pulled back with a jerk. We now observe that the dust particles near the piston are compressed and form a band. This is due to an increase in pressure created by the piston on the particles. This band, called compression, moves towards the other end of the tube as a pulse and dies down. When the piston is pulled back, we observe that the pressure at the compressed region decreases and causes the dust particles to move back to their original position. The low pressure region formed is called rarefaction. Now let us move the piston forward and backward about a mean position with a simple harmonic motion. We see a series of compression and rarefaction bands formed by the dust particles inside the tube, moving towards the other end. These bands constitute longitudinal waves. In a transverse wave, as the wave propagates, each element of the medium undergoes a shearing strain. Elements in solids and liquids have the capacity to undergo a shearing strain. Therefore, transverse waves can propagate through solids and liquids. Transverse waves on the surface of still water are called capillary waves, whose wavelength measures in centimeters only. The restoring force that allows the propagation of these waves is the surface tension of water. Waves formed on the surface of the sea are transverse waves, called gravity waves, whose wavelength is of the order of meters. The restoring force in these waves is the gravitational pull on the water. In a longitudinal wave, as the wave propagates, each element of the medium undergoes a compressive strain. The elements in solids, liquids, and gases have the capacity to undergo a compressive strain. Therefore, a longitudinal wave can propagate through solids, liquids, and gases. During the propagation of a wave through a medium, all the particles of the medium vibrate about a mean position with simple harmonic motion. The displacement of a particle from its mean position at any given time depends on its position with respect to the origin of the wave. This displacement is represented as y of x, t, and is calculated with the help of the four parameters of the waveform: amplitude A, propagation constant or angular wave number k, angular frequency omega, initial phase angle phi, Using the equation y of x t is equal to a into sine kx minus omega t plus phi, where y is the displacement of the particle in the y direction, and x is the x-coordinate of the particle, and t is the time lapsed from the origination of the wave. The displacement equation of the particle is expressed as y of x t is equal to a into sine kx minus omega t plus phi. This equation represents a progressive wave traveling along the positive direction of the x-axis. That is, from left to right. To represent a progressive wave traveling along the negative direction of the x-axis, that is, from right to left, the equation is y of x t is equal to a into sine kx plus omega t plus phi. These equations are obtained from the harmonic circle. A particle is moving in a circular path of radius a, which is the amplitude of the wave, and occupies a position P. The line joining the origin O and P makes an angle theta with the positive side of the x-axis. Drop a perpendicular from P onto the x-axis at point Q. QP represents the displacement of the particle in the y direction. In the triangle POQ, sin theta is equal to y by a. By cross multiplying, we get y is equal to a sin theta. The particles in the medium vibrate with a simple harmonic motion to propagate the wave. Let us consider a point P moving along a circular path with constant angular velocity omega radians per second. Take the projection of this point P on the time meter parallel to the y-axis to obtain the point P dash. As P moves around the circular path, P dash will be moving up and down along the diameter with simple harmonic motion. When the positions of a number of adjoining particles in a medium which are vibrating with SHM are plotted, we get a sinusoidal curve. We can observe a moving sinusoidal waveform by performing a simple activity. Fix one end of a string of length, say 5 meters, to a wall. Hold the free end of the string tight so that the string is taut. When the hand is moved up and down continuously about the mean position with a simple harmonic motion, a continuous wave, which is sinusoidal in shape, travels along the string with the velocity v. Let us mark a point on the string and observe it as the wave propagates through the string. We see that the point moves up and down the mean position. The waveform observed in this process, which is sinusoidal in shape, is a transverse wave. The wave travels in the positive direction of the x-axis. The points of maximum positive displacement are called crests, and the points of maximum negative displacement are called troughs. The maximum displacement of the particles from their equilibrium or mean positions as the wave passes through them is called the amplitude A. As A represents only the magnitude, it is always a positive quantity even if the displacement is in the negative direction. initially. That is, at x is equal to 0 and t is equal to 0. The particle may have positive, negative, or zero displacement in the y direction. When the particle has positive or negative displacement, we say it has positive or negative initial phase angle phi corresponding to the position on the harmonic circle. Wavelength lambda of a wave is the distance in the x direction between any two consecutive repetitions of the shape of the wave. It is the distance between two consecutive troughs or crests, or two consecutive points in the same phase of wave motion. Coming to the propagation constant of the angular wave number k of the wave, consider a sinusoidal wave curve with conditions phi equal to 0 and t equal to 0. Substituting these values in the equation of the progressive wave traveling along the positive direction of the x-axis, that is, y of xt is equal to a into sine kx minus omega t plus phi. Let this be equation 1. It gives y of x 0 is equal to a into sine kx. Let this be equation 2. Let us mark 2 points P and Q which are at the same phase on the wave. Point P is at a distance x1 from the origin, and Q is at a distance x2 from the origin. When equation 2 is applied at points P and Q, at point P, we get y1 of x1 and 0 is equal to a sine k into x1. Let this be equation 3. And at Q, we get y2 of x2 and 0 is equal to a sine k into x2. Let this be equation 4, where y1 is the displacement at P on the y-axis, and y2 is the displacement at Q on the y-axis. As P and Q are in the same phase, they are separated by a distance of one wavelength, that is, lambda. Therefore, y1 is equal to y2. We can now equate the right-hand sides of equations 3 and 4. A sine kx1 equal to a sine kx2. By substituting x2 is equal to x1 plus lambda, we get a sine kx1 is equal to a sine k into x1 plus lambda. This can be written as a sine kx1 is equal to a sine into kx1 plus k lambda. This condition is possible only when k lambda is equal to the product of 2, pi, and n, where the values of n are equal to 1, 2, 3, and so on. We have defined lambda as the least distance between 2 points in the same phase. Therefore, for the least value of n, that is 1, k lambda is equal to 2 pi. K is equal to 2 pi by lambda. Therefore, the propagation constant or the angular wave number k is denoted by k is equal to 2 pi by lambda radians per meter. The SI unit of angular wave number k is radians per meter. As radians are only a number, usually units of k are written as the value per meter. Let us now discuss the period, angular frequency, and the frequency of a wave. Consider the equation y of x t is equal to a sine into kx minus omega t plus phi. Let this be equation 1. By substituting x is equal to 0 and pi equal to 0 in equation 1, we get y of 0t is equal to a sine into minus omega t. This equation can be written as y of 0t is equal to minus a sine into omega t. Let this be equation 2. Points P and Q are at the same phase. That is, one oscillation is completed between points P and Q, and the time taken for this oscillation is called period of oscillation t of the wave. Substituting the x-coordinate values of t at points P and Q in equation 2, at point P, we get y1 of 0 t1 is equal to minus a sine omega t1. At point Q, we get y2 of 0 t2 is equal to minus a sine omega t2. And equating their right-hand sides, we get minus a sine omega t1 is equal to minus a sine omega t2. That is, their displacement will be same as they are at the same phase. The particle of the medium has completed one oscillation from point P to point Q, for which the time taken is the time period t. By substituting t2 equal to t1 plus t, we get minus a sine omega t1 is equal to minus a into sine omega into t1 plus t. This equation can be written as minus a sine omega t1 is equal to minus a sine into omega t1 plus omega t. Let this be equation 3. The above equation is true only if omega t is equal to 2 pi. Therefore, omega is equal to 2 pi by t. This omega is known as the angular frequency of the wave. Omega is also the angular velocity of the point moving along the harmonic circle, from which the sinusoidal wave has been generated. The SI unit for angular frequency omega is radians per second. Frequency is the number of oscillations per unit time made by a particle as the wave passes through it. It is represented by the Greek letter nu and is measured in hertz. Frequency is denoted by the equation mu is equal to 1 by t, which is equal to omega by 2 pi. In longitudinal waves, the particles are displaced in the direction of motion of the wave. The displacement equation is written as S of x t is equal to a sine into kx minus omega t plus phi, where S of x t represents the displacement of the particle in the direction of propagation of the wave at position x and time t. Let us consider a propagating wave that is generated on a stretched string. The initial conditions at the origin are time t is equal to 0, x coordinate x is equal to 0. Y coordinate y is equal to 0 and phase angle of the wave phi is equal to 0. Let us mark a point A on the string. After a time t, the wave has travelled a distance x and the particle A is situated at a distance x from the origin and is now at the crest of the wave. We take a snapshot 1 with a high-speed camera showing the waveform. After an additional time delta t, we take another snapshot 2 and mark point B on the crest of the progressive wave. The crest, which was at particle A, has now moved to particle B. Particle B is situated at x plus delta x from the origin O. Now, let's superimpose the two snapshots. During the time interval delta t, the waveform has moved through a distance delta x. Therefore, the speed of the wave is denoted by delta x by delta t. We have discussed particles A and B, which were in the same phase, that is, the crest of the progressive wave. Now, let's take another pair of elements, say C and D, which are at the same phase. We find that their displacement in the y direction is also the same. Since the wave is travelling along the positive direction of the x-axis, that is, from left to right, the waveform can be represented by the expression y x t is equal to a into sine kx minus omega t plus phi, where k is the angular wave number and omega is the angular frequency of the wave. From the initial conditions, we know that phi is equal to 0. Therefore, yxt is now equal to a into sine kx minus omega t. For particles C and D, y is the same. Therefore, kx minus omega t is a constant. Let this be equation 1. As the wave propagates, the values of x and t between particles C and D are changing. So, to keep the value of k x minus omega t as constant, as x increases, t should also increase. To find the speed of the wave v, we differentiate equation 1 with respect to time t. On further simplifying, we get dx by dt is equal to omega by k, where dx by dt represents the velocity v of the wave. Therefore, v is equal to omega by k. Let this be equation 2. Substituting omega equal to 2 pi by t and k equals to 2 pi by lambda in equation 2, where lambda is the wavelength of the wave, we get v is equal to 2 pi by t by 2 pi by lambda. This is equal to lambda by t. Let this be equation 3. Equation 3 can be written as v is equal to lambda into 1 by t. Substituting frequency nu is equal to 1 by t in the above equation, we get the speed of the wave v is equal to lambda into nu. Let this be equation 4. The speed of a progressive wave is related to wavelength lambda and frequency nu as given in equation 4. As a wave travels through a medium, the particles of the medium have to oscillate or vibrate. Any vibrational phenomenon is associated with mass and the elasticity of the particles of the medium. Therefore, mass per unit length for strings and the elastic property of the material medium determine how fast a wave can travel through the medium. Let us derive an expression to calculate the speed of a transverse wave on a stretched string. The speed of the transverse wave on a string depends on mass per unit length of the string, mu, the tension of the string, T, a relationship between speed of the wave v, mass per unit length of the string, mu, and tension T of the string can be derived by the dimensional analysis method. Let the mass of the string be m and the length of the string be L. The linear mass density mu of the string is equal to mass by length. Therefore, the dimensions of mu are m into L raised to the power minus 1. Tension T in the string is equal to the applied force N. Force is the product of mass and acceleration. Substituting, the dimensions of A are equal to the product of L and T raised to the power minus 2 in the above equation. This is equal to the product of M, L, and T raised to the power minus 2. Therefore, the dimensions of tension T are M, L, and T raised to the power minus 2. Velocity is expressed in meters per second. Hence, velocity can be equated to L into T raised to the power minus 1. Therefore, the dimensions of velocity are L into T raised to the power minus 1. Let us now find the dimensions of T by mu to arrive at the dimensions of V square by substituting the dimensions of T and mu. And simplifying, we get T by mu is equal to the product of L square and T raised to the power minus 2. Let this be equation 1. The RHS of the equation 1 has the dimensions of V square. Therefore, we can write T by mu is equal to V square. On further simplifying, V is equal to C into root T by mu, where C is a dimensionless constant. This dimensionless constant C has been proved to be equal to 1. Therefore, V is equal to the square root of T by mu. This proves that the speed of a wave along a stretched string depends only on the tension and the linear mass density of the string, and not on the frequency of the wave. The frequency of the wave is the frequency of the source which generates the waves. The wavelength lambda is determined by the ratio of velocity v and frequency nu. A steel wire 1 meter long has a mass of 8 grams. If the wire is under a tension of 100 Newton, what is the speed of the transverse waves on the wire? Mass per unit length mu is expressed as 8 into 10 raised to the power minus 3 divided by 1 kilogram per meter. Let v be the velocity of the wave. Velocity is expressed as the square root of tension T of the wire by mass per unit length mu. By substituting the values of T and mu, we get V is equal to the square root of 12,500, which is equal to 111.8 meters per second. Therefore, the speed of the transverse wave through the steel wire is 111.8 meters per second.